So folks, now we're moving on and we're extending this idea of integrals. So previously what we did was we said, hey, in our original formulation of an integral, we took the real number line and we chopped it up into subregions, right? And for those subregions, each one of those little widths we called differential x. So we've got those widths, differential x, and that helps us find the net area between the curve f of x and the x-axis. So this was the one-dimensional integral that we computed in Calc 1. And then previously what we've been looking at in this chapter is taking our some region of our xy plane that we think of as the domain space and chopping it up and using that to help us construct the volume over some function in R3. So we took R2 and we divided it into subrectangles with area differential a, where we could think of that differential a as dx times dy, in order to give us this volume between this surface that we have here. This would be our z of f of xy. That's our surface, and we want to find the volume between that surface and the xy plane. So what are we going to do now? Now we're moving on. So this was just a function of one variable. Now we're going to have functions of three variables. At this point, it actually becomes too difficult to try to visualize what it is we're doing, and we need to sort of trust the process that we've built in order to work with these triple integrals. So we have w is a function of three variables, f of x, y, or x, y, and z. And so just as we took in the one variable integral, we took r and subdivided it into widths dx, or we took R2 in the two variable case and divided into subrectangles of area dA, we are going to take R3, some region of R3, and we're going to divide it up into I'll put cubes for right now, but I'll explain that in just a second, subcubes with volume dV, where dV is dx, dy, dz. Now folks, actually this doesn't have to be a cube. This could be any sort of rectangular prism. Okay. Just like we have here, we've got one width delta x, we've got another width delta y. Those aren't necessarily the same widths as we can see from this image, and we've got another width here, delta z, but this constructs a little rectangular prism. Then we're going to take from within that some representative point and evaluate that in our function to estimate the value of z there. And we're going to adjust, we're going to do that for each one of these rectangular prisms throughout our region in R3. So when we compute this, the triple integral that we're about to describe, in fact, we can write it right here. We're going to say that we're constructing the triple integral over some region, and if we maybe call this, it looks like it's called D, so this is a region in R3. Careful folks, it's not the surface. We're not talking about this surface in R3. We're talking about the solid region formed by this plane, and in this case it looks like we're restricted to the first quadrant, but this is what we're computing here. And what we're computing then is a four-dimensional equivalent of volume. Okay. That's really hard to interpret, so here's something we can do. I find it hard to think about this sort of four-dimensional equivalent of volume or something to that effect, so instead one way to interpret this is to think of this function f of x, y, z, this function of three variables, as being a density function. So at any point in space it tells you how dense the object is. And so if you were to compute the triple integral over that density function throughout your whole region D, then you could think of this as outputting the mass of that region. And well, we might have many other applications for our triple integrals. If you're ever sort of lost for an example, use this example of computing the mass of an object based on a function f that at each point in space tells you the density of that object. And computing that triple integral then is equivalent to finding the mass of that object over the entire region. Okay, that was a little bit heady as far as the description. In the next example, we'll go ahead and just compute a triple integral. So join me in that next video.